TDK Micro POL DC-DC converters are compact, highly integrated point-of-load converters for powering CPUs, MCUs, ASICs, FPGAs, DSP, and other advanced digital logic devices, providing the high-performance, fast-load transient response and high-accuracy voltage regulation needed by these devices. Micro POL converters are high current density power modules that feature a chip-embedded power IC in a thermally enhanced semiconductor embedded and substrate package. Here's what you need to know. Here are the answers to your most frequently asked questions about TDK's Micro POL DC-DC converters. How has chip-embedded technology advanced TDK's Micro POL DC-DC solution?
It's a great question. In order to achieve higher density DC-DC power in smaller dimension, it really requires a paradigm shift in the development approach, particularly number one in IC design, and also number two in packaging and discrete components. Again, all of this is the end goal of creating a sustainable and reliable end solution. This advancement of chip-embedded technology requires a three-dimensional approach of all the components, which includes the packaging design for thermal and regulation performance, innovation of integrated circuit design, and also a close relationship in working with magnetic and the discrete component development. As an example, TDK's micro point of load uses a semiconductor in substrate, or C-sub, where the packaging is built around the IC to minimize parasitic interconnect losses, and at the same time providing optimal thermal design. This technology has increased current density over other approaches by as much as 4 times to 8 times in similar size. The end result is you end up with a compact regulator design with higher current delivery in a smaller PCB footprint. In addition, the reduction of external component building materials, or BOM, and overall reduction in board space. TDK's micro point of load offers the best-in-class in power density using chip-embedded technology today. This visual depicted here shows you, in fact, the cross-section of the chip-embedded micro point of load technology at TDK, where the actual die is embedded into the C-sub layers, semiconductor in substrate layers, and the packaging, including the heatsink, is built around the integrated circuit, and then we work very closely with our inductor teams and also the external capacitor teams to create the entire power module design in the smallest form factor and also the smallest height. And as a result of that, TDK is able to achieve the best power density per unit area and unit volume. This shows a summary, for instance, of the FS1412, our 12-amp power module, and also our FS1406, our 6-amp power module, with a completion with on the left of each of these, you can see the artistic rendition of the power module, but then actually in an actual circuit design. For instance, here, the FS1412 12-amp power module is coming at a current density of 65 amps per square inch, or an incredible current density, including the height dimension of 1,025 amps per cubic inch. The 1406 6-amp power module on the right is showing a current density of 50 amps per square inch, or an incredible current density of 850 amps per cubic inch. This is the best in the industry today and the impact of chip-embedded technology with TDK's micro point of load.
If I'm using a power plane in my PCB, why is point of load important? Can the TDK Micro POL be used to meet the FPGA AC transient versus load specifications?
Absolutely. The purpose of point of load is to provide precision power delivery with DC and AC accuracy to the target FPGA, ASIC, system on chip, embedded processing devices, and other peripheral IC devices. Each target device has a target tolerance band for voltage specification accuracy. The overall DC-to-DC solution must meet these specifications for proper system operation. As an example below, it is common to see DC voltages of 1% DC accuracy, and typically a AC accuracy of plus or minus 2% AC ripple to 3% accuracy. These are typical requirements in modern embedded control design for core voltages ranging now from 0.4 volts to 1 volt, especially on 4 nanometer and 7 nanometer ASICs and SoCs. So this little graphic here kind of gives you an example of what we mean by DC voltage and AC plus ripple specs. It gives you what we call the tolerance band of both DC and AC accuracy as you develop your total power solution with your power modules and external components. And yes, these are typical FPGA AC transient load specs that I mentioned here at 1% DC and AC ripple of 2 to 3%. These are very common for Xilinx and AMD, as well as Intel, the Altera FPGAs, and most other FPGAs and SoCs in the market today.
Can the TDK Micro POL be used for low DC ripple applications like FPGA SerDes power rails?
Yes, absolutely. And actually, you can use pretty much any DC to DC, either discrete or module today. It's very common. But this question gets frequently asked because primarily 10, 15 years ago, they were using primarily LDOs, regulators. The currents of the SerDes or serial deserializer, these are the high-speed serial deserializer rails in FPGAs today, has increased in current. What's happened there is you have a large number of SerDes lanes, high-speed serial lanes, passing data at tremendous speed rates. So yes, it's common for TDK micropole devices to be used in SerDes power rails. Typical SerDes designs, for example, require usually sub 10 millivolts peak-to-peak ripple. In addition, large FPGAs today may have a requirement of 4 amps to 20 amps plus for multiple SerDes lanes. Hence, space and compact design is also important in the overall power design areas. So as an example, here we show an actual plot of one of TDK's microphone of loads where we actually designed it for low SerDes. And here you can see the ripple specs here coming in here at sub 10 millivolts peak-to-peak ripple. In fact, we're able to achieve even sub 5 millivolt peak-to-peak ripple effective amount of output capacitance. And these typical specs typically are involving load step. In other words, how fast they want the voltage and current to ramp, as well as a slew rate, typically from 1 amps per microsecond to 10 amps per microsecond. So this is an example of the end results of using TDK's microphone of load. And yes, they can be used for the SerDes lanes, which is also an important part of the power of the overall FPGA power designs.
How is the module thermally enhanced to be effective?
This actually is one of the most important aspects of chip-embedded technology by TDK. The TDK microphone technology uses a copper redistribution layer appended to the semiconductor IC, and this is used as a heat plate. So what happens is we bring to the surface with our IC designers the hottest portions of the die, primarily the upper and lower MOSFETs and the driver. This heat plate is then connected via design layout through the substrate layers of TDK's C-sub packaging technology. Again, remember, this is semiconductor in substrate packaging technology. And this allows for an optimal connection to the bottom pins of the package without adding any superfluous material that might impede thermal flow from within the device to the actual PCB or board design. This has allowed TDK's microponal devices to operate at higher temperatures without the need of airflow at higher board temperature ambience. Examples, the FS1406, which is in 3.3 by 3.3 millimeter and 1.5 millimeter heights, can actually handle 6 amps up to 15 watts. And the same is true for the 1412 in excess of 21 watts and 30 watts. This is actually incredible current density. And density is only as effective as you can take the heat out of the package. So this technology allows us to do a really advanced thermal enhancement to allow the airflow and also the thermal flow to flow through the device almost 4 to 8 times better than most of our competitors.
Is there a list or a table of common micros and FPGAs that mate to specific TDK modules?
Yes, over the last few years, TDK has been working on several reference designs. We have several reference designs, in fact, with AMD Xilinx. In fact, we have some more upcoming in 2023. And this also includes reference designs and starter power schematics for various FPGAs and SoCs in the market today. An example I show here below is a design we did with a Xilinx Alliance partner with Xilinx. We also have other designs with Intel Power Solutions are also available. Some of the customer testimonies as you look at this design highlight TDK's microcontroller advantages of compact power design and high current density without airflow, and also better output current ratings over temperature. As you look closely at this system on module below, this actually is a Xilinx Zinc 7 module about the size of your ring finger, coming in at 43.7 by 17.8 millimeters. You can see the simplicity of the build of materials of these three power modules, which, by the way, are 7 by 6 millimeters. This entire system on module, in fact, requires no airflow even at high temperature. And below here, you can actually see a thermal plot of the hottest point, which actually is in between the modules. So what we're trying to test here is to show how close we can bring the power modules. And this also demonstrates the simplicity of design and the thermal capabilities of the design as well. This is the FS1406 and the 1403 used with a Zinc 7 from Xilinx as an example. We also have, to assist customers, tables of some of the most popular FPGAs in regards to our TDK micropoint of load. As you look at the different charts here, here's a chart for the AMD Xilinx FPGAs from the low range to the mid range to the high end of Xilinx FPGAs from Artex, Spartan, the Zinc series, the Kentex and Vertex, and the Vertex ACAP series. We're actually working on a Versal ACAP reference design for next year using our upcoming 1525. This is our 25 amp device. The other devices are all fully available. Here we show you the currents and voltages that are atypical of these FPGA designs. Also, we have a chart for the Intel, previously the Altera FPGAs, expanding from the low end, the Max 10, all the way to their flagship FPGA called the Agilex SoCs. And as another entry, Lattice. Lattice tends to focus on more system on chip focused on camera applications. This is their ICE40, Crosslink, and the SerDes applications. We just added this recently. The main point of all these charts is to show compact power design options for the FPGAs, which is a very important trend in the future as system density and the areas for power shrink, and having these tiny chip-embedded power modules becomes a system-level advantage of board reduction and simplicity of materials.
Thank you so much for sharing, Tony. To learn more about the technology discussed here, visit Mouser's website.